We now start section 1.4, the matrix equation. So previously we saw that if we had 3 or 4 vectors, let's say a1, a2, a3 vectors, and then we have a vector b, then we can find some unknown quantities x1 or numbers such that x1a plus x2a2 plus x3a3 is equal to b. So we x1, x2, x3 are unknown, which we want to find to see if b can be written as a linear combination of a1, a2 and a3. So this is called vector equation. So now we can actually create a matrix equation by putting these vectors a1, a2, a3 as columns of the matrix A. So in that case, we have the matrix A, which is of size m by n, and the x vector, we have now x instead of the these x1, x2, x3, these are put in the vector form and they are constitute the vector x, and the b vector is over here. Note that the size of b vector and the x vector are not the same, so x has to be to match the order. The size of x has to match the size of a, in the sense that a is of size m by n, then x has to be of size n by something, but since it's a vector, so it has to be n by 1. So these numbers, because we are going to write it as ax, so the number of columns of a must match the number of rows of x in order to multiply them. So what happens, the resultant will be b. So we are saying a times x is equal to b. So this is called the matrix equation, and so size of a is m by n, size of x is n by 1. What will be the size of b? Whatever is left. So from here m is left and from here 1 is left. So the size of b is m by 1. So ax is equal to b is called the matrix equation and can be written like this, and again can be expanded like this. So you see now this is the same as the vector equation. So vector equation and matrix equation, they are basically the same thing. Now we have a theorem. If A is an m by n matrix with columns a1, a2 up to an, and if B is in Rm, then the matrix equation Ax is equal to B has the same solution set as the vector equation is. So as I just said, they are equivalent to each other. Okay, which in turn has the same solution set as the system of linear equations whose augmented matrix is this. So whenever you have to solve a vector equation, it means you have to apply the row operations on the augmented matrix, and same thing if you have to solve the vector equation, same thing you have to do. So note that the equation Ax is equal to B has a solution if and only if B is a linear combination of columns of A. So the matrix equation Ax is equal to B will have a solution only if and only if the vector B is a linear combination of the columns of A, and vice versa. So now we have a theorem 4 that if let A be an m by n matrix, then the following statements are equivalent. Equivalent means if one is false, all of them are false. If one is true, then all of them are true. So first one is for each b in Rm, the equation Ax is equal to b has a solution. Okay, so so the second statement is each b in Rm is a linear combination of columns of A. So if if 1 is true, then 2 is true. So if there is a solution, Ax is equal to b has a solution, then each b can be written as a linear combination of columns of A. And if each b can be written as a linear combination of columns of A, then it means Ax is equal to b will have a solution. Then third equivalency is that the columns of A span Rm. So the columns of A will span the space Rm. And then fourth is A has a pivot in every row. So if A has a pivot in every row, the columns of A will span Rm. If columns of A span Rm, then every B in Rm can be written as a linear combination of A. And then every equation of the form Ax is equal to B will have a solution, and every row will have a pivot, so and so forth. So let us now look at examples. The first example is let A and B be as given. Does equation Ax is equal to B has a solution? Or you can be asked, can B be written as a linear combination of A? So here is our A matrix and here is the vector B. So what do? We basically just solve the augmented matrix. Okay. So or because now I wrote it like this, so since we have to find out whether B can be written as a linear combination of columns of A. So let X be x1, x2, x3 vector. Then Ax is equal to B gives us this, and which can be then written as a vector equation like that. So we want to find x1, x2, x3 such that B can be written as the linear combination of columns of A. So we take the augmented matrix, apply the row operation. That's what I did here, and in the end I came up with this matrix in the reduced row echelon form. So which gives us the values for x2, x1, x2 and x3, which means this one has a solution. So Ax is equal to B has a unique solution. That's what we found. Now the question asked us, does equation Ax is equal to B has a solution? So we have answered that yes, it has a unique solution. Then it says, can B be written as a linear combination of A, of columns of A? So yes, because of theorem 4, since B has a unique solution, it means A, and also we note that A has a pivot in every row. So by theorem 4, Ax is equal to B will have a solution for every B, and therefore every vector B can be written as a linear combination of columns of A. Every vector B of size 3 by 1. Second example, let v1, v2, v3 be these vectors. Does v1, v2, v3 span R3? So does this set, the set of 3 vectors, span R3? So we don't have an augmented matrix here because we don't have a extra vector B. So we just take the vectors v1, v2, v3 and put them in column in a matrix. Put them as columns of a matrix, 3 by 3 matrix, and apply row operations again. So we note here the first entry of the first row is 0. We want a non-zero entry here. So in the first column, the only non-zero entry is -2. So I will switch the first row with the third row. That's what I did in the first step. Now I want this first entry to be, this one to be 0. Sorry, to be 1. So I divide by -2, or I multiply by -1/2. So I get a 1 there, so which is our pivot. So this, we have a pivot here. And then we carry the row operations, and ultimately in the last step here, so I didn't go ahead and complete the row reduced operations to get it in the row reduced form. I just stopped when it got into the reduced form, or row echelon form, sorry. So I see pivots in all 3 rows in the proper positions. So it means by theorem 4, v1, v2, v3 will span R3. So we can write it as v1, v2 and v3 span R3, or we can say span of v1, v2, v3 is equal to R3. Okay, one more example. Let A be this given matrix. Then we have bunch of questions here. How many rows contain a pivot position? Do columns of A span R4? Do columns of A span R3? does the equation Ax is equal to y have a solution for each in R4? And can every vector in R4 be written as a linear combination of columns of vectors of A? So we can answer these only once we have converted into row reduced form, or yeah. So I start with the matrix A here, apply the row operations as you can see, and I end up getting here, and we see that we have a row of zeros, which means not every row has a pivot. So only 3 rows have a pivot. So the pivot is over here, here, and here. So we see the third column does not have a pivot, which was the column for x3. So x3 is a free variable. So not every row has a, so the first question was how many rows contain a pivot position. So only 3 rows contain a pivot position, the first, second, and the third row. So we can just set only 3 rows. We don't have to tell the number. Only 3 rows have a pivot. Second part is, do columns of A span R4? Well, according to theorem 4, since not every row has a pivot, so the columns of A do not span R4. Now we have 3 pivots, so it seems logical to question, okay, it means 3, can this, the columns span R3? So answer will be no, because the size of the columns is 4 by 1. So the columns belong to R4, so they cannot span R3. And C part is, does the equation Ax is equal to y have a solution for each y in R4? Well, again, by using theorem 4, we can say that since every row does not have a pivot, so by theorem 4, the equation Ax is equal to y will not have a solution for each y in R4. And the last question, can every vector in R4 be written as a linear combination of the columns of column vectors of A? So answer will be no, because not every equation Ax is equal to y has a solution, so not every y in R4 can be written as a linear combination of the columns of vectors A. So only the, applying row operation, all the answers can be given based on the row reduced echelon form of the matrix that we have. Okay, now we will move on to section 1.5.